This video is about substances and mixtures. We're going to talk about what is meant by these terms in chemistry and how we can distinguish between them and why it's important to know the difference between them. So substance is a word that we use in everyday non-chemistry life that can just mean a generic material that we may or may not know what it is, or we're just trying to describe something generic. But in chemistry, substances always refer to something that is pure. And the purity of that material is based on how many molecules, how many different types of molecules make up that particular material. So there will only be one type of particle. If we have something that is made of molecules, there will only be one type of molecules. Sometimes we have a material like, say, helium gas, that helium doesn't form molecules, so it's only made of one type of atom, and there are no molecules. So within the category of substances, we can distinguish these between elements and compounds. And this is kind of a molecular view of what we might mean. So these balls represent different elements. The different colors signify that we have a different element involved. So in the first picture in purple, we have what might be a noble gas like helium, where it doesn't really combine with anything, and that would be called an element. But in the second one, we have pairs of yellow balls. And those yellow balls together form molecules. So this might be like nitrogen or oxygen or fluorine or chlorine or hydrogen. Each of those elements are what we call diatomic, meaning two atoms. But we still refer to this as an element, even though that it has molecules. There's only one type of atom. And in the third group, we have, or in part C, we have a representation of molecules as signified by balls of different colors, both black and blue. And in each of those, we have one black one at the middle and three blue ones around the outside. They're all arranged the same way. So we would call this a pure substance, but a compound, not an element. Now, in chemistry, we distinguish these three things that we call pure substances from mixtures. So on the far right, for letter D, you can see an example of a mixture which has lots of different kinds of particles in it. Now, pure substances can be distinguished from pure substances can be distinguished from mixtures in that they can't be separated by a simple physical process. So I can't filter them to separate them. I can't just boil one off. I have to do a chemical reaction in order to separate them. And that's because it will either require us to break bonds or form bonds or perhaps both. Okay. So here's an example that you might find in your kitchen. On the right-hand side, we have baking soda, and on the left-hand side, we have baking powder. And you may not know that there is a difference or what that difference is. But if we look at the ingredients, we get a hint of that. So the ingredients for baking soda is just one thing, sodium bicarbonate. So having only one ingredient, that tells us it is a pure substance. The only molecules in that box are sodium bicarbonate molecules. On the other hand, if we look at the ingredients for baking powder, we have cornstarch, sodium bicarbonate, which is baking soda, sodium aluminum sulfate, and monocalcium phosphate. And each of those ingredients has their purpose in baking powder, but it does make baking powder a mixture. It is no longer a pure substance. Now, when we're trying to distinguish different kinds of mixtures, what we really want to know is how well mixed it is. So we can classify our mixtures as being homogeneous, or sometimes it's pronounced homogeneous, which means the same throughout. So the prefix homo means the same. And so what might be a homogeneous mixture? Well, in chemistry, we call these solutions. So usually when we think of a solution, we think of something dissolved in water. And the particles are so spread out that each individual molecule of the thing we dissolved, what we call the solute, each individual molecule of the solute is completely surrounded by water. So as a result, there aren't any big particles that can cause light to diffract off or bounce off in weird ways. And this makes those solutions very, very clear. All gases are also considered, when we have mixtures of gases, all of those mixtures are going to be considered homogeneous. And this is because the particles are so far apart that they can't really clump together at all. So they always mix very, very evenly. So we expect that anywhere in a room is going to have the same level of oxygen as anywhere else in the room. It is mixed very, very evenly. And then, as I mentioned, anything that is dissolved in water, if it is a solution, it is going to be clear, meaning that we can see through it. Now, it may have a color associated with it, but it will be clear. We can see through it. It's not going to look foggy, and it's not going to look opaque. There's another group that are not water-based. If we have metals, we might mix metals together and have a solution. And of course, they wouldn't be clear because metals just aren't clear. But we call those alloys, and alloys are solutions. So if I mix together tin and copper, I'm going to end up with bronze, and that is considered a solution or an alloy. And there's lots of different kinds of alloys that we might have. In contrast, if we have a heterogeneous mixture, we have different parts that might have different ratios. So we might think of this as being something chunky, like a chocolate chip cookie. Or if we're thinking of something that is more on the molecular level, when we have lots of proteins gathered together or lots of sugar molecules gathered together that are not separated by the solvent, then those are considered heterogeneous. And usually those are going to be big enough particles that they are going to start to scatter the light. Another indication is going to be if we have more than one phase. So I'll give you an example of that in just a minute, but our phases are solid, liquid, and gas. So if you have a liquid with gas in it, for example, seltzer water or Sprite, all those bubbles in there are places, localities where there's a lot of gas molecules, where nearby there's a lot of water and sugar molecules. So we would call that heterogeneous. It's not the same throughout. There are locations high in concentration in gases and locations that are high in concentration of sugar and flavor. So if we have something that is water-based, that looks like it's pretty much the same throughout, an indication that it might be a heterogeneous mixture is that it's cloudy or opaque. So for example, milk, you can't see through it. And so it is going to be a heterogeneous mixture. So here's an example of another heterogeneous mixture that we might call chunky. This would be a salad that depending on where you put your spoon or your fork to lift up a bite, you're going to get different things in that bite. So it's heterogeneous. It is not the same throughout. So if we take a look at marshmallows, these are an interesting example because they seem like they're pretty much the same throughout. But if we think about what phase they are, we have to think for just a minute because the material holds its shape, but it is compressed easily. And that's because the marshmallow itself, the sugar and the proteins that make up the marshmallow are in a solid form, but they are a foam around a gas. So there's little bits of air in tiny bubbles all throughout the marshmallow. So all of those little bubbles throughout the marshmallow are in one phase, a gas, whereas all of the sugar and proteins and flavor are going to be in another phase, a solid. So anytime you have a foam, whether we're talking about a styrofoam cup or we're talking about marshmallows or whipped cream, whenever you have a gas dispersed throughout a material, whether that's a liquid or a solid, that's an example of a heterogeneous mixture. All right, so some examples are some defining differences here. Pure substances, all of the particles or molecules will be the same. In mixtures, they will be different. We will have different ones. Might just be two, but it could be tons of different ones. In a pure substance, the chemicals can't be separated from one another, or the elements can't be separated from one another through simple physical means. We have to do it chemically. We have to have a chemical reaction to separate the carbon from the oxygen and carbon dioxide. Whereas with mixtures, we can separate those physically. Maybe we can filter them. Maybe we can evaporate off the water and leave behind some residue. We can also do chromatography. So those are some of the defining differences. Now, with pure substances, one advantage of them is that they're easier to work with theoretically. We only have to think about what one substance is doing at a time, and we can write a chemical formula for that particular material. So if I can write a chemical formula for it, it's going to be a pure substance. And so it's easier to write that into a chemical equation and to figure out how much of a material I'm going to get. And so we like to, in chemistry, work with pure substances. Unfortunately, most of the world is made of mixtures. Almost anything you interact with is going to be a mixture of some kind. The air, in fact, is a mixture of nitrogen, oxygen, argon, and carbon dioxide, and a little bit other gases as well. So there's very few examples of where you would find naturally something that is just one pure substance. And so we need to be able to distinguish when we're talking about something reacting, whether we're talking about the substance within a mixture or the mixture itself. Okay, so what I'd like to do at this point is look at a couple of examples, see if you can figure these out. When I look at white grape juice, is this going to be a substance or is this going to be a mixture? So remember, your defining characteristic here is, are you looking at something that is only one kind of molecule in that glass, or are there lots of different kinds of molecules? So while grape juice just comes from grapes, it does have water in it, and it has sugars in it, it has tannins in it, it has citric acid in it, it has tannic acid, so it has lots of different kinds of chemicals. So that tells us that it is a mixture. So now that we know it's a mixture, can we determine whether it is a homogeneous mixture or a heterogeneous mixture? So the key thing here is to look at the glass. We can see through this material very easily. Since this is a transparent mixture, it is a clear mixture, that tells us that this is a solution. All right, example number 2, sugar. So table sugar has the chemical formula C12H22O11. You can see a picture of it there. Is this going to be a substance or a mixture? So the key thing here is we have a chemical formula, and that chemical formula tells us that all of the molecules are exactly the same. They all have 12 carbons, 22 hydrogens, and 11 oxygens. And because of that, it is a pure substance. All the molecules are identical. Now, is this pure substance a compound or is it an element? So we can tell that there are 3 different elements involved in this chemical formula, so this would be a compound. All right, and our last one here is orange juice. Is orange juice a pure substance or is it a mixture? So just like with the white grape juice, the orange juice is going to have in it some water, it's going to have in it some sugar, and it's going to have citric acid and ascorbic acid, and it's going to have all kinds of different materials in there. So this is going to be a mixture. So now we need to determine, is this mixture a homogeneous solution or is it heterogeneous? And again, we're going to be looking at whether or not we can see through this material. And you can tell that there is an orange that's kind of peeking out behind the glass, but is not visible through the glass. So orange juice is opaque. We can't see through it. And so since it is opaque, that tells us that this is a heterogeneous mixture. The clusters of perhaps pulp or perhaps other materials that are in the orange juice are large enough that they scatter light, so they're not completely surrounded by the water, and that makes this a heterogeneous mixture. Now, I'm not too concerned with whether or not you know things that are like juices, whether that is heterogeneous or homogeneous, but you should be aware of foams in particular as being heterogeneous because they contain both a gas and a solid or a gas and a liquid.